Group 7. Now, when you say Group 7, we're studying here the chemistry of chlorine, bromine, and iodine. You know the Group 7 has a fluorine, chlorine, bromine, iodine, and astatine. There are 5 elements in the Group 7, but we study only the chemistry of the chlorine, bromine, and iodine. We don't study fluorine, we don't study astatine. The reason is the fluorine is the most reactive halogen, whereas astatine is radioactive, right? So all these halogens, when it's most reactive, the reactions are very violent and unsafe to be carried out in the laboratory. And also when fluorine reacts and forms the very strong compound, so that compound will be highly stable. So therefore, fluorocompounds are very stable and very hard to react further. So therefore, we don't study fluorocompounds, and fluorine itself is highly reactive. So astatine is radioactive. So all these halogens, they all poisonous, and they all have a similar smell, very strong smell. They're all nonmetals, and the boiling points of these halogens, they increase down the group, because you know these halogens, they form diatomic molecules, chlorine, bromine, and iodine. So the intermolecular attractions determines the boiling and melting point as well as the physical state of these halogens. So the physical state of the halogens increases or changes down the group as the boiling point increases. The chlorine is a gas, bromine is a liquid, and iodine is a solid. The reason why the physical state increases along with the boiling and melting point is that the strength of the intermolecular forces. Now, when it comes to simple molecules, the intermolecular forces determine the physical properties such as boiling point, melting point, and the physical state. So they all form diatomic molecules, and this fluorine is a pale yellow gas, smelly and poisonous, and fluorine is a pale green, bromine is a brown liquid, iodine is a gray solid. You can see the intensity of the color increases as you go down the group. You can now write the description of these halogens. Fluorine is a pale yellow gas, smelly and poisonous. Chlorine is a pale green gas, smelly and poisonous. Bromine is a brown liquid, red-brown liquid with a brown color vapor. Bromine is a red-brown liquid with a brown color vapor, smelly and poisonous. And iodine is a gray solid. Iodine is a gray solid with purple vapor. There's no iodine liquid. When you heat iodine, it sublimes to a gas. So iodine is a gray solid with purple vapor. So as I mentioned, the physical state of the halogens changes from gas to liquids to aqueous solids or solids, and the reason for this is the strength of the dispersion forces, increasing the strength of the dispersion London forces down the group. We'll be discussing under the intermolecular attractions about the factors which affect the strength of the dispersion force. That's the number of electrons. As the number of electrons increases, strength of the dispersion force increases. So you know, chlorine to bromine to iodine, the number of electrons increase. As a result, the strength of the dispersion force increases. That is the reason why the boiling and melting points increase down the homologous, down the halogens, as well as the change in the physical state. From gas has the weakest intermolecular force, then comes the liquids, and the solids have the strongest intermolecular force. And these halogens dissolve in water to form strong acids, right? Chlorine dissolves in water to form hydrochloric acid and hypohalous acid. Hypohalous acid is chloric 1 acid. It's a reversible reaction. The same reaction is seen with bromine as well. But iodine is insoluble in water, but if you keep for a long period of time, it slowly dissolves. But iodine is soluble readily in hot water. So when iodine dissolves in water, it forms aqueous iodine. The color of the aqueous iodine is a red, yellow, you can say yellow-brown. It's a yellow-brown solution. But if you dissolve iodine in organic solvent, that gives a purple solution. Remember, iodine solid is gray. When you heat iodine, it sublimes to form a purple vapor. If you dissolve iodine in water, you get a yellow-brown solution. And also when you dissolve iodine in organic solvent, you get a purple solution. So all the halogens, they show similar chemical properties. The reason is the number of electrons in the outermost shell, because all the halogens have 7 electrons in the outermost shell. As the number of electrons in the outermost shell is equal, they all show similar chemical properties. As for the reactivity, because they have 7 electrons, the reactivity depends on how easy the halogens can gain electrons. How easy the halogens can gain electrons. So the size of the atom increases as you go down the group. So therefore, ability of the halogens to gain electrons decreases down the group. The smaller ones can gain electrons with ease, meaning fluorine can gain electrons with ease. Therefore, the fluorine is the most reactive halogen. As for the iodine, is the least reactive. Don't start with astatine. Iodine is the least reactive because it takes electrons lesser, lower extent because of its less effective nuclear attraction. So reactivity decreases as you go down the halogen group, right? So we know halogens, as they gain electrons, they undergo reduction, because reduction is gaining of electrons. Oxidation is the loss of electrons, right? So metals undergo oxidation, while metals lose electrons, as we discussed last week, whereas non-metals, they gain electrons and undergo reduction. Now when it comes to the halogens, they undergo reduction, therefore they are good oxidizing agents, right? Because the oxidizing agent itself undergo reduction, right? So the strongest oxidizing agent among the halogens are found at the top of the halogen group, which is the fluorine, and the weakest oxidizing agent is found at the top. That means oxidizing or reducing power, I would say, will decrease as you go down the group. The top one can undergo reduction easily, right? And these halogens, if you analyze why we call them as halogens, because it's actually a Greek word, halogen. Halo in Greek means salt, gen means former. So salt formers, because halogens, when they react with the group 1 and 2 metals or any other group metal, it forms the salt. Right? That's the salt former. It means halogen. Halogen in German means, in Greek means salt former. So this halogen becomes halogen because they all form ionic salt and combine with the metals, right? So electronegativity of the halogens, we know the fluorine is the most electronegative element in the entire periodic table. So electronegativity will in fact decrease as you go down the group, right? So halogens, they react with S-block metals, like for example sodium, to form sodium chloride salt, right? All these salts are ionic, they are white solids, and similar reaction is seen with any group 1, group 2, say magnesium reacting with bromine, similar reaction, magnesium bromide. You can notice the metal changes its oxidation state from 0 to +1. That means metal get oxidized. That proves that the halogen is oxidizing agent, because halogen changes its oxidation state from 0 to -1. So that undergoes reduction. So that is oxidizing agent. In these two examples, you see the halogen undergoes reduction, and that shows that the metal is a strong reducing agent, the halogen is a strong oxidizing agent. So as you go down the group, it becomes weaker. The top ones are strong. Please copy these two reactions. Halogens show displacement reactions. What is meant by displacement reaction is that the more reactive halogen can displace a less reactive one from its salt. Now look at this reaction. The chlorine is more reactive, right, because it's up above bromine. So the more reactive chlorine can displace the less reactive bromine from the salt to form KCl and Br2. See, The more reactive halogen has displaced the less reactive halogen from its salt. Salt is KBr. So these are referred to as displacement reactions. But the less reactive bromine cannot displace more reactive chlorine. The backward reaction will not take place. Likewise, chlorine reacting with Ki forms KCl and I2. The more reactive halogen, chlorine, has displaced the less reactive one, chloriodine, from the salt. But the less reactive iodine cannot displace the more reactive chlorine. The backward reaction will not be feasible, right? So likewise, another example, bromine reacting with Ki, right? The more reactive bromine can displace the less reactive iodine. So these reactions, displacement reactions, can be used to show the relative reactivity of the halogens, right? The more reactive one displacing the less reactive one from its salt.
Here we are with a series of halogen halide ion displacement reactions. In the first three conical flasks here we have potassium chloride, in the second three conical flask we have potassium bromide, and in the third set of three conical flasks we have potassium iodide. Into each of them we're going to sequentially put iodine in this row, bromine water into this row, and chlorine water into this row. So let's have a look if any displacement reactions occur. Here's the iodine. You can see it stain the bottle deep brown colour. We're familiar with iodine, and if we place an approximate equal amount, a few mils, into each of those solutions, we see not much difference in the three. Same colour for the iodine, and nothing appears to have happened. Into the second sequence of flasks we're going to put bromine water. So this is quite nasty stuff. There's the bromine water. Quickly put the stop top back on the bottle. The bromine water, 0.02 molar. And let's introduce that into the three flasks. So we've got into the first flask, which is in bromine water in potassium chloride. This is bromine water into potassium bromide. And finally bromine water into potassium iodide. And hopefully you can see there that the bromine into potassium iodide has turned a much deeper orange colour than the other two, perhaps indicating a difference in the reaction. Finally we have chlorine water. Here's the chlorine water, and we're going to introduce that into the three flasks. So first let's put some chlorine water into the potassium chloride, then chlorine water into potassium bromide, and finally chlorine water into potassium iodide. So once again you can see a difference in the intensity of the colours there. The chlorine into potassium chloride, no noticeable change, but both into the chlorine into the potassium bromide we've got a development of an orange-yellow colour, and into the potassium iodide we've got that familiar iodine colour present there. So,
was the video clear? You saw the displacement reactions of potassium halides, adding chlorine, bromine, iodine to potassium chloride, bromide, iodide. You notice that color change. A color change is the indication that the halogen which you added is more reactive than the halogens present in the salt. That's called the displacement reactions. Please copy these three reactions. So next we'll see what happens when these halogens react with water. Now, as I mentioned before, these halogens, they dissolve in water, especially chlorine. It forms the acid, as I mentioned before, hypohalous acid, that's HClO, which is also referred to as chloric 1 acid. Hypohalous is the common name, and hydrogen halide, which is hydrochloric acid, right? So this is very important reaction. This is why we add chlorine to the water, disinfect water, and also to kill that is to kill the bacteria and to prevent the growth of the algae. In fact, this chloric 1 oxide is also a powerful oxidizing agent. Even this chloric 1 oxide kills bacteria. Please copy the reaction. So the reaction with chlorine is also the same, but remember, iodine does not react with water. With hot water it reacts rapidly. You get a solution of yellow-brown color, aqueous iodine, but with cold water it's a very, very slow reaction. These halogens, they also react with sodium hydroxide. The product of the reaction of halogen with sodium hydroxide depends on the condition, meaning the condition meaning here whether you're under hot conditions or whether it's under cold conditions. Now here the reaction usually takes place under cold condition. Under cold condition you get sodium chloride and sodium chlorate 1, which is sodium hypochlorite we say. This is the household bleach, not the bleaching powder. The bleaching powder is calcium chloride. That is chlorine reacting with calcium hydroxide. Calcium chloride is a bleaching, CaClO. The sodium chloride is used as a liquid bleach. In laundries, you have, for laundries they use liquid bleach. This is sodium chloride, soluble chloride, right? Okay. That's under cold conditions. You can write the reaction, similar reaction with bromine as well as iodine. Please copy this. Now, when the conditions change from cold conditions to hot conditions, a further oxidation of chlorate 1 takes place to chlorate 5. Now, for example, chlorine in the presence of NaOH under hot conditions, you get NaCl. Instead of NaClO, you get NaClO3 plus water. Instead of NaClO, you get NaClO3 plus water, right? Now, let's see how to balance this. You can see the chlorine here is plus 5 oxidation state. You can use the oxidation state method to balance this. Otherwise, you can simply balance it this way.